Yeah, so anyway, chapter 25 is about the standard model of particle physics. And at the first part, we had a bit of history here. What was surprising for me personally is that actually in 1928, the only particles which were known to science were electrons, protons, and photons. It's kind of surprising because it was not so long time ago, actually like 100 years only. Yeah, anyway, and yeah, so I've been talking about the chapter 25 in short. So in short, basically we had some history there. And afterwards, in the next subchapter, we have talked about the what is called like two spinor representation of the Dirac spinor. So basically, in Dirac equation, we have a wave function or kind of like spinor-like quantity psi on which gamma matrices act. And as you can see here, it could be represented as a pair of two spinors. Yeah, and that representation kind of leads us to the Zitterbewegung representation, which is kind of those zigzaggy things. So basically, electron is traveling all the time with the speed of light, but having that zigzag trajectory kind of slows down a particle on the average, and therefore electron speed is slower than the speed of light. But actually, instantaneous speed of the electron is the speed of light. And what you are seeing here is what's called electron propagator. So basically, it's kind of all kind of superpositions of different scenarios of the trajectory for the electron, which happen in like kind of simultaneously. Yeah, and kind of evolution goes and goes by that kind of indeterministic basically process, right? Because yeah, so a lot of different scenarios will kind of be layered up. Yeah, and Penrose also tells us here that usually in physics people or either do not know or do not use the two spinor representation. Usually they use what is called like left-handed helicity part of the Dirac electron or Dirac spinor, and they use that special gamma 5 here, which is like minus I and all the gamma matrices here multiplied onto each other. So it's kind of the projector we have seen in the Chris lecture on the spinors. Yeah, and afterwards Penrose just jumps into the Electroweak interactions and talks about the reflection asymmetry in there. And what is that? It's he has just been talking about the kind of that the weak force bosons, W or Z bosons, will not act on the Z part, which goes to the left here. The weak force will only act together with the Z part of the particle. And therefore, kind of, there is an inherent asymmetry into how the weak force interacts. Yeah, and that leads to the non-intuitive and interesting conclusions to which Qian-Xun Wu, I think, came experimentally in 1957 in the experiment with those cobalt-60 atoms here. Yeah, and basically that experiment proved that if you will take a mirror and place it, then the reflection of our physical system will not be kind of good enough physical system. So like if you reflect the zigzag particle, you will need also to change the charges. So instead of just doing parity transformation, you also will need what is called like charge, I think. Yeah, C invariant. Yeah, so it's charge conjugation. So you will need also charge conjugation to turn the particle in the mirror to its antiparticle, and antiparticles, they will react into different ways. So the ZAC now will be reacting with the weak forces in the mirror. So basically weak force acts good enough well, if you use the CP symmetry, but if you use parity symmetry, which Wu's experiment showed us, you will not have the good physical system in the mirror. And it was astounding because never before people have seen or like have seen such a process. Yeah, also in this subchapter there was a little bit about neutrinos, about the Weyl equation. So basically Weyl's equation is the same decoupling equations we have had in the two-spinor formalism before, when splitting up the Dirac spinor into two. But now you can see that the coupling constants are now zero here, so the two equations kind of decoupled, and Penrose talks here that actually only the unprimed version of the neutrino, so it's kind of left-handed one, will react with the weak force, and right-handed one will not. Yeah, and afterwards he just says that we don't have a good criteria for the antiparticles. So basically I will just write down that we had some history, we had that psi splitting like into alpha A and some beta A spinors, and afterwards we talk about like weak force asymmetry and zigzag picture. I will just put a zigzag here. Yeah, and afterwards we need kind of to talk about the criteria for the antiparticles, and to have that we need to talk about the CPT theorem, about three like symmetries in physics. One is charge conjugation symmetry, which kind of inverses all the charges prescribed to the particles. P is a parity symmetry, which is just like mirror reflection or like space-like symmetry, and T is about the time symmetry. So basically PT together is a space-time symmetry, and C is charge conjugation, so it's all about the charges. Yeah, so, and therefore now we can come up with the criteria for the antiparticles. And particles and antiparticles are actually related with PT symmetry, or just C if you believe into CPT theorem. So basically you can think about those as particles moving backwards in a space-time, and that's kind of similar to the picture Feynman used. He been talking about the antiparticles as particles moving back in the time. Yeah, and Penrose just give us a recipe here. He just tells that we can now just state, probably I think that it is the information taken from experiments. So he just tells us that we should think about leptons, and leptons are electrons and their families, like muons and tauons, and also corresponding neutrinos, and also quarks. So leptons and quarks, they are particles. And therefore, if you use PT symmetry, reverse them in the space-time, or charge conjugate those, you will have the anti-leptons and anti-quarks, so basically antiparticles. And leptons and quarks will react with the weak force using the zig part of the zigzag, and antiparticles will react with the zag part, so other way around. Yeah, and afterwards Penrose goes straight to the symmetries. He talks about U2 symmetry actually. So he talks about U2 symmetry, or which is the same as SU2 multiplied by U1 symmetry. We know that U1 corresponds to the electromagnetic force, and SU2 here kind of corresponds to the weak force. So U2 is like the upper theory here, and it's called Electroweak symmetry or theory. Yeah, so that's Electroweak symmetry basically. Yeah, there are different debates on like which group should be used here, which is the correct one. Penrose tells us that actually he thinks that, and his colleague actually pointed out to him that U2 is like the best group to use here and to think about the particles. And he actually shows that to us using Hermitian matrices in there. And like basic information hiding behind that symmetry is that if you take any kind of like superposition of basic bosons, so we have for weak force we have W plus minus and Z0 boson, and here we have photon. I think it's noted with gamma, right? Yeah. So we have 4 particles, 4 bosons, and that U2 symmetry means that you kind of can rotate any superposition into those particles. So basically we can substitute any of that boson with some kind of superposition created from those 4 particles. And Penrose, for example, tells us that, for example, we can have like Y capital instead of our gamma as a photon if you, for example, take some kind of superposition for Z0 and photon. Maybe some coefficients should be present here, but anyway. So that's kind of the main idea here. But the question is, if we have such a nice symmetry, then why we observe only those 4 and kind of fixated bosons and not the other kinds of superposed particles in there? And Penrose tells us that actually for the particle to be observed, it should be what is called an eigenstate of the mass. And he also tells us that that's kind of tricky concept, but the like conventional view onto this is that this big U2 symmetry was true only a small amount of time after the Big Bang, and afterwards it was ruined, which is called like spontaneous symmetry breaking. I will just call it like symmetry breaking. So, and in the process of the symmetry breaking, yeah, so those 4 bosons were kind of on the same rights with other superpositions and other bosons, basically in that kind of particle group, particle space. But afterwards, like Higgs field was kind of frozen, and it gave some of those mass. We know that photon is massless, and those 3 bosons, they have masses. And that frozen Higgs field kind of gave the masses to those and leave out the photon. And because of that, kind of we have the freezed out like broken symmetry, which is not observed in the nature in reality, but it's kind of was there. And it's I think that its roots lies into the possibility of grouping those 4 bosons into Hermitian matrix. So like Hermitian matrix structure is actually like 2 real numbers which you can think about like the particles which are the antiparticles for themselves, and they are Z boson and photon, and the W plus and W minus, they are kind of complex conjugates of each other, and therefore you kind of having that nice Hermitian matrix which is preserved by the U2 group symmetries. Okay, so that's it. Yeah, Penrose said that he will talk more about Higgs field later, and that was kind of the end for the Electroweak theory here. Yeah, and afterwards we came to the strong interacting particles. Let's also recap those.
One thing maybe, could you show the figure 25.5? I think that's a nice illustration of what you talked about with the Feynman's arrows, the time direction of antiparticles that you mentioned. If we have these white arrows, the direction we can read. I think we could read from this if they were antiparticles and traveled in time. You can explain it better, I think.
So you're talking about that anti-neutrino in the beta decay, right?
Yeah, I was actually thinking about the white arrows, but that's an electron and not.
No.
It doesn't really make sense.
White arrows, they correspond to the charges. So electron has a negative charge, therefore it has a white arrow pointing backwards, and proton has positive charge, so it's it's not that arrow, and the arrow where the particle is flying indicates either it is a particle or antiparticle. So antineutrino actually moves backwards in time and in space.
It's the black arrows.
Yeah.
That indicate if they're antiparticles, and the time direction they seem to be traveling.
Yeah. So C symmetry, charge conjugation will reverse the directions of those white arrows. And if you reverse P, that's interesting, but I'm not sure if probably together, like if you reverse PT, then those arrows will be reversed. I think those black ones. But I'm not sure about that, 100%.
Actually, shouldn't it be the white ones? Because wasn't the charge conjugation equal to PT? And charge conjugation is the plus or minus charge. So PT should be the same as that. No?
Yeah. It seems true. So you just need to reverse all the charges. Yeah. So it's kind of hard on the diagram because it's hard for me to say how is that connected actually to the space. So is it in space only or is it in space-time? Probably in space only, right? So time is just the trajectories
I
here.
think time direction is roughly upwards, not like these hourglass diagrams that are specific, but this is, I think, roughly time is up.
Yeah. Anyway, let's go further to the strong interacting particles.
But no space.
I have one complication to add for the SU2 cross U1. They don't neatly break into, like, SU2 is the weak force and U1 is E&M. The reason is that you only end up with 3 gauge fields for SU2 cross U1. And I mean, as you brought up, the photon and the Z are actually just different linear combinations of those fields. But yeah, so you only end up with 3 fields there. And what you do is kind of the same thing that you do with like spins, where you have a triplet and a singlet. And so that triplet represents the weak force and the singlet represents E&M. Are you hearing me okay?
Yeah. I've been thinking.
Well, so yeah, if you have U1 on its own, the conserved quantity is electric charge. But when you have SU2 cross U1, what you have is the isospin and hypercharge, so, which is not the same as just like pure electric charge or pure spin. So you end up with those three gauge fields. I think you did a good description of it. I was just pointing out that like one of the first things that you wrote down when you decomposed U2 into SU2 cross U1, you wrote that SU2 was the weak force and U1 was the E&M force.
Yeah.
But I don't think that you can decouple it like that because the Z and the photon are actually linear combinations of the few gauge fields that are there.
Yeah, so like it's kind of the emergent theory, right? So we cannot decouple it like purely, and we will have different superpositions in there instead.
Right. Yeah. So we end up with three gauge fields from SU2 cross U1. And with those three gauge fields, we can make a triplet, which is the W plus and minus and the Z, and a singlet, which is the photon.
And what is a triplet? Just like three-dimensional vector or something?
Yeah, I mean, so this is where it's related to spin and why they call it the isospin. Because like, if you had two spin half particles, you could add them together, and if they're if they're aligned, then they go into like a J equals 1 state, and then there's the M equals 1, minus 1, or 0. That's a triplet, right? And then there's the J equals 0 state where M could only be 0. And so that's like a singlet state. So the math is very similar. You have
so you will have different representations, and therefore you will have either like singlet or triplet representation.
Yeah, so that's that decomposition into weak and electromagnetic forces. Is the weak force forms this triplet, and the E&M forms the singlet.
Yeah.
So one thing I've been confused about, when people talk about isospin, it doesn't have anything to do with spin other than the math is the same, like it's not actual spin. I'm kind of confused about why it's called isospin.
Yeah, I mean, that's probably the best way to put it, is that it's just the math is the same for isospin. It's not like a magnetic moment idea or anything that's related to like a fundamental particle's spin, but it follows the same structure and representation theory, so they call it isospin.
Yeah, that would be interesting to read somewhere in the additional sources, maybe in Physics from Symmetry, I don't know. Need to take a look at that later.
Yeah, it's probably a piece of history why they called it isospin, but the thing that comes to mind is that the math is the same.
Yeah, actually, we are approaching to the strong force where we will have a lot of those strange namings, for quarks and colors. So I think we should continue. Let me add some lights. Okay, so strongly interacting particles. So the theory of the strong force is called quantum chromodynamics, and chroma means color, but that kind of has nothing to do with the ordinary concept of the color. And actually, we will talk while talking about strong force. We should to talk about hadrons or hadrons, of which neutrons and protons are particular examples. So, and hadron is just the massive basic particles of nature, and they are divided into two families, baryons and mesons. Yeah, and baryons are fermions and bosons mesons are bosons, and all of those are hadrons. Okay. Okay, so, and I have a small, like, kind of Venn diagram here. So we have, like, fermions here with F capital, and we have some part, like a subset called leptons, which we have talked before, like electrons, neutrinos, all those families, muons, tauons, and they are non-strong interacting particles, so they do not interact strongly. And all of the other fermions, as far as I know, or I think from that subchapter, are baryons. So they're kind of bigger, therefore, but maybe let me take a look. So baryons are ordinary nucleons, and their higher cousins called hyperons. Okay. Yeah. Yeah, and probably baryons are at least, so they are hadrons, and also they are fermions. Therefore, they lie here in the intersection here, and they are the fermions which interact strongly. So I don't know if they are kind of fill up all of that circle, or do we have something here like none being the baryon and none being lepton. Joe, maybe you can answer that.
Sorry, my network was cutting out. What was the question?
Yeah, I just asked about the fermions here. So I have a set which is called like capital F, and it describing the whole like set of the fermions. And I have leptons as this small subset on the right, and baryons here on the left. And my question was, do we have something like except those? Something more between like other type of fermions which are not baryons and not leptons?
Yeah, the quarks.
Ah, quarks. Okay.
Yeah, all of the matter is fermions, and then the leptons are like the electron and the neutrino, and the other two generations have the same thing. And then the quarks themselves, which make up the hadrons.
Okay, so quarks are here, and baryons are just like more evolved matter created from quarks, basically. And we will also have a mesons, and mesons, they are bosons. Yeah, and actually, like a vast number of hadrons have been discovered in cosmic rays and in accelerators. That's true, and actually, like the whole theory of the strong interactions came out from those discoveries, I think, because those absorbed particles from the accelerators, they were absorbed, or like they were absorbed to fall into certain families called multiplets, and those multiplets were kind of symmetric under the group SU3, or more correctly here SU3 quotient by the Z3, so just a group from the three elements here. Yeah, and initially that symmetry was about the flavors. So the whole theory was based on the quarks, and those quarks were divided into three types, three flavors: up, down, and strange. And baryon was taken to consist of just three of these, and meson of one quark and one antiquark. Okay, and they have also that strange property that they have non-integer charges here. And Penrose says that perhaps largely because of these implausible seeming values for the quarks' electric charges, they were not kind of like people were not happy with the theory initially, and they thought about that as just like convenient bookkeeping and nothing more. But anyway, the theory predicted new particles, and actually also it had some consequences, and strange consequence of that was that our quarks, which are fermions, should be considered or thought of as the bosons actually. So, and it's kind of weird, like why should we do that? And Penrose gives us an example here. So he says that if quarks were treated as fermions, that those kind of particles should collapse, for example, because we have 2Ds here, but it doesn't. And also we have a symmetrical relationship, because like UUD is not distinguished from UDU here, so it's the same particle actually in terms of like strong force theory. Yeah, and because of that, we will need more instruments or like some kind of approach to tackle that conclusion, which kind of contradicts the spin statistics theorem, which I hope you'll see something more about it in the chapter 26. Okay, any questions before we will go into 25.7? Okay, so let's continue. So basically to fix up that problem, people came out with the notion of the color for quarks, and they demanded that each flavor of quark should also come in 3 colors, and that any actual particle composed of quarks must be completely antisymmetrical in the color degree of freedom. Yeah, and this antisymmetry passes over to the quark states themselves, so that antisymmetry between individual quarks gets effectively converted into symmetry in a 3-quark particle. Okay, so basically they fixed up that problem with those colors. Yeah, and the colors are never to manifest themselves in free particles, so color is in an essential way unobservable, and any free particle is actually color neutral. So if we have some kind of a particle, we have 3 different versions. Yeah. So he just says here that we have 3 different versions for the delta plus particle, depending on the colors which we will have for the UUD decomposition of it. And the antisymmetry in the color degree of freedom for actual free particles ensures it, he says. Okay, so yeah, it's kind of hard to track down for me currently, like to say more about those relationships between symmetries and antisymmetries here, but I'm just thinking about that as just like a special new degree of freedom to allow the bosonic behavior for the quarks, for those compositions of quarks for the triplets, I think, and just for quarks. So instead of being fermionic, we are kind of making them to act in a more symmetric bosonical way, I think. And afterwards Penrose told us that usually colors are red, white and blue, but he's not happy with it, so we will use red, yellow and blue instead. Okay, so yeah, and he says that there is indeed a symmetry here that goes well beyond mere colors. There is to be a full a real-dimensional SU3 color symmetry in which R, Y, and B provide merely one set of basis elements for the vector space on which SU3 matrices act. So our before we had symmetry based on the flavors, and now we will have a symmetry based on the colors. And he says that we will have therefore a lot more quarks now, so we will have 9 quarks, 3 flowers multiplied by 3 colors. But actually in standard model situation is twice as bad because we will need to add 9 more. So we need 3 more flowers here called charm, bottom, and top. And therefore together we have 18 independent quarks. Yeah, he doesn't say why those should be added or created. So I don't know why do we need those. Joe, maybe you can add something here.
Well, it's mostly just because the particle zoo. They found particles with a whole bunch of masses that were all just hadrons, and then they had different. So they classified these things in the multiplets that he mentioned, and there was this whole idea of the eightfold way. That was kind of taken from Buddhism.
From Buddhism, yeah.
And so what they did was they were trying to make like all these nice geometric shapes that described the particle properties, where like, you know, the horizontal axis would be the charge and the vertical axis would be like the spin, or you know, you could also arrange it by other quantities, and one of these quantities that they were interested in was the strangeness, and that's why we had to add the S quark, right? Because the U and D were enough to cover protons and neutrons and pions and all sorts of stuff, but you needed another particle to describe all these other things in the zoo that we were seeing.
Yeah, so basically they've been getting more and more particles from the accelerators and experiments, and they needed to explain those.
Yeah, they had a few hundred particles before they had really come up with a nice theory for the strong force. And so going from a few hundred particles to 18 particles is actually pretty nice.
Yeah. Okay. So, and afterwards Penrose tell us that actually introducing color, if it was only introduced for the tackling the problem with the boson fermion behavior of the quarks, it seems that it's not like good enough, and it looks a bit artificial. But he says that we have really great reward here, because he says that we can introduce using that SU3 color symmetry, we can create a gauge theory based on the SU3 color group. So we can kind of create a gauge theory, which we have seen. So basically it's kind of a group attached at every point of the space-time. So we have, so any gauge theory is kind of like a fiber bundle where every fiber will have a symmetries, and those symmetries will be described by those gauge groups. And gauges are kind of our symmetry freedom, basically. So if you change the gauge, nothing will change in the real world. Yeah, so, and the theories for the groups such as SU3 or SU2 are called Yang-Mills theories. I need to put the book a little bit up so you can see those. Okay, and this indeed is the basis of the quantum chromodynamics, and the idea of those like gauge theories is to modify our notion of the derivative on our manifold, introduce appropriate covariant derivative in there, fix up derivatives with some kind of the gauge potentials, as we have done in the electromagnetic force case with that IE and A capital, so it's electromagnetic potential thing. And basically all the forces will come up as the curvatures of like defined by the covariant derivative on that fiber bundle on the manifold. Yeah, and basically that's kind of beautiful in terms of math and mathematical theory of physics. And I guess that Penrose kind of is saying that it's kind of great thing to have. I don't know why we couldn't have used like the previous SU3 group based on the flavors here, but probably there was some reason. Maybe in the later paragraph we will see more about that. So we can now ask about the gauge bosons, so just like bosons for a strong force, what are those? And the gauge bosons for the quantum chromodynamics are called gluons, and gluons will basically kind of be propagators of the strong interactions. And he also draws a few diagrams here, and as you can see, one of those is three-pronged diagram, and we have seen in the previous subchapters that those kind of diagrams could be only in the non-abelian theories with non-linearities. So he says mathematically it is telling us that we will have some kind of non-linearity in our group. Okay.
Yeah, that vertex makes the strong force just so intractable.
So interactable?
Intractable.
Meaning
like
intractable.
it's just, yeah, it's because this figure A there, what happens is if you go to like the next higher order, well, this gluon could, produce a pair of gluons, and then those pair of gluons could annihilate into another one, right? You could imagine using this vertex in B twice, inserting it in A, and that would give you like a higher order diagram. But you could continually, everywhere that you see a gluon line, you could replace it with another 3-gluon vertex to get a higher order term. And what happens with the strong force is that these things actually continue contributing.
Oh, so you will have kind of the diamond shape, right? In the middle.
Yeah, and it could be totally fractal. You could draw in another diamond on any one of these gluon lines.
It kind of reminds me about Twin Peaks of David Lynch. He had similar symbol, I guess, for the owls there.
Yeah, so this is very different because you never see a 3-photon vertex.
Yeah. So it kind of connected also for the confinement, right?
Yeah, it kind of determines that it's a short-range force.
Mm-hmm. Yeah, thank you. That was interesting. Yeah, because we haven't had yet, or like me personally, I haven't had like a lot of experience with those Feynman diagrams. I hope maybe while studying the next chapter on QFT, we will get a little bit more into those, but we'll see. So let's continue. And
by the way, there was also a SOG. There were, zigzag, but there was also a SOG that he mentioned in the 11th footnote in this chapter.
Could you repeat, please, because there were some cuts, I think.
Okay, it's in section 4, the subchapter 4, and there's a footnote. He refers to there, number 11 footnote, and there he mentions something called SOG also. Besides SIG and SAG, there's also a SOG. That's non-spinning.
Yeah,
Yes.
it seems I haven't read that. So, massive particles of spin 1 can be described as having three ingredients. Left-handed Zig, helicity 1, right-handed Zag, we have seen those, and non-spinning Zog. Interesting. Let us say the Zig 2 spinner and the Zag 2 spinner has two unprimed indices and two primed indices. Yes, they have different two indices because so I have drawn them wrong on the paper. Anyway, respectively, while the Zog2 spinner has one of each, we may take the view that it is just the Zog particle that mediates the weak interactions.
It's quite interesting that it would be a mediator.
And it was in 25.4?
Yes. It was referred to from there. Yeah.
I'm trying to find it.
I think it was more towards the end of that subsection.
Yeah, I'm looking there. Yeah. The situation is complicated by the fact that there are also entities of spin 1 involved in weak interactions. And spin 1 particles, they will be also like two spinners, right? And he is talking that those bosons could be sort of as Zogs or something.
Yeah, because they also mediate the weak force, so that would make sense. Right?
Yeah, interesting, but it's kind of hard to wrap the head around that currently because it's kind of the part of the two-spinner calculus, I think, or something. Okay, so and why did you recall about the Zog here? I'm not sure how to connect that with the strong forces.
No, it's not connected with this part. I should have mentioned it earlier.
Oh, okay. Just an interesting fact. Yes, thank you, because otherwise I've missed that. I've never heard about dogs before, so it seems I've skipped it.
Yeah, we didn't cover it last time. I was thinking that also, yeah.
Okay, thank you. So let's move further. In the next paragraph, he says that the main role of the group SU3 in the standard model has moved from the flavor symmetry that it had in the 1960s and 70s to the color symmetry of the present-day standard model. And in fact, in this standard model, the three flavors D, U, and S are not now fundamentally grouped together at all. Instead, so before we had them grouped into triplets, but now we have triplet because of these three colors, I think. And instead, they kind of regrouped the particles, or like constituents for the bigger particles, for the hadrons. And now we have the groupings other way around, and we have three generations of the doublets, like down and up here, strange and charming, bottom and top, I think. And the notion of having three generations applies also to the leptons, and the generations being that of the electron, the muon, and the tauon, and their corresponding neutrinos. So we have, it seems that we have like three generations of matter for some reason. And question is why it is that magic number 3 here. I've heard that question or saw that in the Physics from Symmetry book also, and it seems that Eric Weinstein also is talking about this third generation, right, Joe?
It was an illusion.
Yeah, the pseudo generation, supposedly.
Yeah, but kind of like, why do they call those or that pseudo generation? So what is the reason behind it?
Well, yeah, so it's just because they all have the same math. If you just treat it like, so the first generation forms a doublet, and you can think about that as like, the up and down states for like a spin half particle. This is why it's like isospin, or why they call it isospin, is because, up and down are like spin up and spin down. And so you can create particles that have isospin 1/2. Well, those are fundamental, and then isospin 1 would be um, particles that you can make out of ups and downs. Um, and then, even further, you can get isospin 3/2, or uh, you can build up these composite particles just from ups and downs. And the math of it is exactly the same as adding spins,
Mm-hmm.
or like adding spin halves.
Mm-hmm.
And any particle that you could make from ups and downs, if you made the same combination from charms and strange, then it would follow the same math. So that's why they call it generations, because the only real distinction in terms of like how they behave is that the second generation is heavier than the first.
Mm-hmm.
The third generation is heavier than the second.
Mm-hmm.
But ultimately, the math is the same. They all behave like spin up and spin down states. There's just 3 copies of them.
Yeah, really, really interesting. Really interesting. Maybe you know where I can read about that in terms of the connection between spin, or it is hidden basically in the isospin notion, and I can just read about isospins, I think, and weak forces.
Yeah, I mean, all my recommendations are going to be like standard particle physics textbooks.
Mm-hmm.
Like Thomson does a really good job of explaining, well, like, what is isospin.
Thompson?
Yeah, so I don't know his first name, but Thomson, Modern Particle Physics. It's from Cambridge Publishing.
Maybe you can write a short list of your top favorite standard physics books. Just mention them if you like.
Yeah, that sounds good.
Yeah, I
But
also
like your go-to references.
I also have some hopes to get to the physics from the symmetry book and kind of go through it fully one day. I think it will also contain similar information on those isospins and connection between the matter and spin mathematics in there.
Yeah, and Kerman posted the Thomson's book.
Oh, great, great. Thank you, and let's move on. Yeah, and now we are coming to the angles, to the interesting interactions between different forces. So Penrose just says that there are complicated interrelations between the strong and electroweak interactions. In particular, there are certain rotation angles between the basic entities that are recognized by strong interactions and those recognized by weak interactions. And he shows it on the example of the K0 meson. I always speak in French here, like meson. I will try to draw something here. So he says that we have like K0 meson, and also its antiparticle, like that K0 is a hat above or something. And those are strongly interacting particle coming up from the strong interactions. So they are kind of governed by the strong forces. But after some time, they decay, and they decay weakly. And K0 meson will decay into like KL or KS meson, either one of those. And afterward, that will also decay into 3 pions, and that one into 2 pions. And the scene is that this and this also, like KL and KS, they could be thought of as the combinations, superpositions of the K0 and K0 hat, or that dash particle. So you can think about KL as K0 plus K0 is a hat combination, basically. And therefore, you can kind of flip. So he says each of KL and KS is a linear combination of K0 and its antiparticle, into which K0 can flip by means of weak but not strong interaction. So K0 can flip into KL or KS using weak interaction. And he says that the rotation between the strong interaction basis states K0 and K0 is a dash, and the weak interaction basis KL and KS. So you can see it here. So basically we have two different basis states. Two of those are those K0s, and two of those are KL and KS. And he says that those two bases will have an angle between them. And that angle is called Cabibbo angle, which is about 15 degrees actually, or 0.26 radians. And the same angle features in the interrelations between strong and weak interactions generally. So it doesn't depend on the particular particle we have used in the example. So for other mesons in which we have interrelations between weak and strong force, we will observe the same angle. So it's kind of encoded into the relationship between strong and weak forces, electroweak force. And we have a similar angle, which now features in the interrelation between weak and electromagnetic interactions, and forms an integral part of the electroweak theory. It's called Weinberg angle, or the weak mixing angle. And it is kind of similar to the Cabibbo angle, but there is a difference in the roles between those, because Weinberg angle it was the angle which was frozen in when U2 symmetry of the electroweak theory was broken at about 10 to minus 12 seconds after the Big Bang. But Cabibbo angle doesn't have such a status in the standard model, and therefore we should kind of preserve that distinction in our minds between those two angles in the boundaries of the standard model. And at the end we have a full blown basic symmetry group of the entire standard model, which could be taken as SU3 by SU2 by U1, quotient by Z6 here. So cyclic 6 group. Okay, any questions for this?
Are these angles like a constant of the universe, or I'm a bit confused about these.
Yeah, they're a constant of this one. There's some weirdness. There's a weirdness about broken symmetries, because broken symmetries are usually like degenerate. Like you could pick a variety of states, and we just happen to land in one of them. So it's going to be difficult to make a prediction for what this angle would be, but it's easy to measure.
Okay.
Maybe you'd say a constant in space, but not necessarily a constant in time.
Yeah, that's what I think.
Okay, so if I meet a friend from another universe, they might have a slightly different Weinberg angle.
Exactly.
And they might also be a lizard man because of the Weinberg angle being different.
Yeah, they may have like no chemistry.
Could be that one.
But yeah, these angles, what they tell you is basically like how the we had this discussion like a few weeks ago about the difference between the mass eigenstates and flavor eigenstates. Um, uh, so these angles are related to that sort of discussion. Like you can use the Weinberg angle to estimate the difference in masses between neutrinos, because we don't have a way of predicting the mass of the neutrino, but we can tell you that there's a difference in mass between the different generations, and you could use these angles to determine that.
I forget if they mentioned it in this book. I was reading about like W0 and B0 bosons. Does anyone know what those are? Is it related to like before symmetry breaking or something?
Well, those are the two states that form your two like neutral superpositions. So the W0 and B0, if you add, I may have this backwards, but if you add them, you'll get a photon, and if you subtract them, you'll get a Z0.
So they are just superpositions, right?
Well, yeah, you get three gauge fields. Yeah, so there's the B, the W, and then the charge W. And by taking those combinations of them, that's how you can form, like what I was talking about before, about the triplet and the singlet state. And it is like almost exactly the same math as when you add two spin halves, right? You take the Bell state with a plus sign, and that's like the J equals 1, M equals 0. And then the Bell state with the minus sign is the J equals 0, M equals 0 states. Is that clear? Or I mean, it would also help to like either write it down or look at a Clebsch-Gordon table or something like that. But you know, there's the two Bell states where you have a plus sign and a minus sign, and both of them have like that M equals 0.
Yeah, I think I know what you're talking about. I kind of wish, like, he keeps talking about linear combinations. I kind of wish he had actually, like, written out some linear combinations and showed us what he meant instead of just talking about it. But,
I
well,
think
I could dig through my notes.
maybe there
might be.
should be some in the Thompson book, so we can kind of glance over in there.
Yeah, they're definitely in Thompson. I could dig them up from my notes as well.
Yeah, and if you want, we can try and not jump right away into QFT, but let's talk about that at the end of the call. So I propose to continue with the next subchapter, which is called Beyond the Standard Model. And here Penrose talks about the that like one could adapt a perspective on the Cabibbo angle corresponding to the to that taken for the Weinberg angle. So basically their relationship. But this would require something beyond the present day standard model. And he says if you want to somehow kind of unify the angles, we need to use a larger symmetry group, which will include SU3 and U2 together. And such theory is referred to as a grand unified theory, or GUT, or GUT, I don't know, good. So there is no commonly accepted grand unified theory, but there have been many attempts, and the main ones being based on SU5 or SO10, and we have heard about SO10 from Eric, I think, or the exceptional group. I think it's how that guy was called, like Leary or
Gareth Lisi.
Lisi, yeah. So it seems that Lisi was working on the E8. Yeah, and he also says that has something to say about these matters also, and some remarkable implications of certain great unified models will be considered in the chapter 28. So in any case, standard model is clearly not the ultimate answer. It isn't final because it has a lot of rect edges, despite its undoubted success, and it involves about 17 unexplained parameters that simply need to be taken from observation, such as Cabibbo and Weinberg angles, the masses of the quarks and leptons, and a number of other features. Also, there is the rather strange asymmetry between the roles of SU3 and U2, in that SU3 is taken to be exact, whereas the U2 is actually broken. And to be a gauge group, it would seem to require an exact unbroken symmetry. So it's kind of weird here. And Penrose says that he knows about like one more way to address the issue, and it is the dual group or dual groups theory created by the Qianhong Mo and Zhu Xiongcun in 2002, and it is husband-wife team, and in their scheme each non-abelian particle symmetry group has a corresponding dual group, which is the same abstract group as the original one, but which plays kind of the opposite role. And you can recall give a few seconds for a phone to focus. Yeah, okay, so you can recall the dual of the Maxwell tensor, which we have seen in chapter 19. And we can imagine a dual of U1 gauge connection that has the dual Maxwell tensor as its bundle curvature. And the idea is to do something similar for the remaining symmetry groups of the standard model SU2 and SU3. But since these groups are non-abelian, it's not possible simply to regard the corresponding dual curvatures directly as bundle curvatures again. So there's some kind of the more complex approach here and sophisticated thing to be done. But anyway, they somehow are doing that. And actually, into those pairs of dual and like regular group, one of those will be exact and one of those will be broken group, like with a broken symmetry. And therefore we will have kind of symmetries restored into our theory. So now we will have and he also says that confinement, for example, which we have for the exact symmetry, will also be in the other cases. So for a new exact SU2, we will have some kind of the new kind of the confinement, which will be two-colored lepton confinement. And we will have new kind of the particles there, and those subparticles will be very heavy, which is why they have not yet been detected, and why leptons appear as point particles at present-day energies. So I'm not sure about point particles here. And why they appear as a point particles at the present-day energies. So it's some kind of practical result, I think. Sorry, give me 1 second. I think I should. Yeah, maybe that will sound better. Okay. So, and and in this theory we will also have the broken SU3 counterpart. And what's kind of amazing here is that those scientists and that theory can actually go down from 17 unknown variables just to these 3. So that new theory has only 3 adjustable parameters, and from those 14 more follows, and all of the mathematics of the standard model kind of follows up from those. And as Penrose says, this strikes me as a definite step forwards, provided that the predictions of the scheme are borne out. So it's interesting if we already have some kind of the predictions of that theory confirmed in practice. Need to Google that. I don't know the answer for that question. Yeah, and anyway, Penrose isn't sure about the SU2 group in the conventional attitude in the standard model, because SU2, like how SU2, if it's broken, could be a gauge group. So he says it should be exact, and it is not, so it's kind of seems like a hack to him, I think. And he says that in the conventional approach, we are thinking about that as a spontaneous symmetry breaking, and it's a conventional picture. And as we will see in chapter 28, some unpleasant implications follows up from that. And chapter 28 will be about the Big Bang. So let's wait and see what awaits us there. And in the next chapter about QFT, we shall be seeing something of the exotic but essential mathematical ideas that lie behind the way that symmetry breaking is presently handled in the standard model. So we will learn a little bit more also. So that's it. Any questions, additions?
I think I could elaborate on the issue with SU2 not being an exact symmetry. There's the idea with SU2 is that the particles that are like up and down, or like electron and neutrino, in order for it to be a proper SU2 isospin symmetry, what happens is it requires that those two particles have the same mass. So in this case, the electron would have the same mass as the electron neutrino, and the up would have the same mass as the down. And this is just not true, like observationally.
Mm-hmm.
And so the way that they get around this is actually by including the Higgs field. They say, well, yeah, you know, the electron and the neutrino, they really do have the same mass. However, once a symmetry is broken, that introduces this new Higgs interaction that ends up giving the electron more mass than the neutrino. And so this is that kind of unpleasant artificial nature to it, is that, you know, you think about it and you say, well, no, the electron does not have the same mass as the neutrino, and no, the up does not have the same mass as the down. So what were people even thinking? Because what's really interesting is they came across these symmetries decades before they had really come up with the Higgs. So it's so interesting that they would jump to this and actually run with it, right? And continue developing theory on top of it, because just observationally, the up weighs differently than the down. And similarly for the electron and neutrino, they just have different masses. So it's really kind of displeasing.
Yeah, interesting.
Do they attach Higgs to other similar particles, elemental particles, or are there any problematic particles similar to electron and neutrino?
I think I don't understand the question. Is the question like, does the Higgs have other particles that are the same mass? Are you asking about like an isospin with the Higgs? Or?
No. If I understood you correctly, you said that they used Higgs to give more mass to electron.
Yeah, that's right.
In YouTube. Yes. So have they used Higgs to other particles to have the similar effects?
Yeah, it affects every particle. So like Higgs field.
But but I mean to solve a similar problem.
Ja, discrepancy to account for it.
Yeah. or are there actually any other problematic particles in U2?
Yeah, so the all the fermions get their mass from the Higgs. And the reason is because we are assuming this SU2 isospin symmetry. We're like that is, core to the standard model. It needs the SU2 isospin. And for that to be the case, the up has to be the same mass as the down. And the electron has to be the same mass as the neutrino. So really, we're kind of like asserting that this is true. And then we come in and glue everything together with the Higgs later.
Sounds like a hack.
Yeah, it's unsettling, isn't it?
Or ad hoc?
Indeed.
Yeah,
How about the antiparticles? They are not mentioned in the standard model. When they group all these 16 different and plus Higgs plus maybe gravity. So what would all the quarks, leptons, everything antiparticle on anti-side?
You cut out at the end there, but I think the question is like, does each antiparticle also interact with the Higgs? And the answer is yeah. So we would have these terms where like the electron interacts with the Higgs, and then we would also have these terms where the positron interacts with the Higgs.
yeah, and
Okay, that was good. I didn't actually ask this, but good addition.
yeah,
I was just thinking if the other particles, every particle in the 16 plus 1 plus Higgs plus gravity, they all have
I think,
behavior.
Mark, I think that eventually it doesn't matter because we have those like CPT symmetry, and if you convert like using PT or C, if you convert your like physical situation into the particle, like every particle to its antiparticle, it will just follow the same rules. So like mass will be the same.
Okay.
And I think that's the reason why we haven't seen any, almost haven't seen any antiparticles. So we have seen antineutrino, for example, in beta decay, right?
One more clarification to this. Does Higgs particle have an antipart,
Maybe it's
like anti-Higgs?
maybe it is the same way as a photon is antiparticle of itself, but I don't know much about Higgs boson.
Never heard of a negative of it, at least.
Yeah, there's also some weirdness. I hope that Penrose goes into this. There's like the Higgs, the one that we talk about, is just like one aspect of it. The Higgs itself is more than just the one field. I think it's 4 real fields or two complex fields.
Okay, so you're talking about Higgs as in the Higgs field, and it's not only one Higgs field, but then we also have the Higgs particle. It's a manifestation of the field, so it's easy to get things confused here.
Right, exactly. Like similar to how we were talking earlier, there's kind of 2 fields that make up a photon, right? But we observe the photon.
Right.